Welcome back, everybody. The longest subterranean river in the entire world exists in the Philippines. Uh, I don't know where it is. Everybody, when I showed it earlier in the second hour, everybody thought Palawan, but I don't know for sure. But the water's pretty. Yeah. So when they talk about a subterranean cave, Puerto Princesa, there's apparently a park, like a national park in the Philippines, where I don't know if I love the language of calling this a subterranean because obviously it's like a cave, right? So, but the cave isn't completely underwater. There's like an archway here that you're gonna float through, or else all these people would drown. So there must be something. But cool. You've been here? Is it? Is it super cool? It looks really cool. Is it near Palawan? It is the same spot. Okay, cool. Yeah, it looks really nice. Neat. Apparently, it will amaze you. Did it amaze you? You were amazed? Cool. All right. Okay, that's not true. Filipinos can eat without rice. Like, I've seen people eat not rice, but most stuff is rice. Yeah, that makes sense. All right, here we go. Drives me absolutely crazy. I don't remember what side of the room I had to do what. FO 1.1. What did you guys get? 33? Okay, how about 1.01? Is the next one 3003? Or, yeah, 3003? Okay. Half the room, you didn't probably get those numbers. I'm not going to make us do it, but if we went and did 1.0001 and we just added one more zero, which means we're getting closer to the number 1, right? What do you think is going to happen? Probably just add another 0 in between, right? 30,003. Okay, and as we keep getting closer, arbitrarily close as we want, because I can always get closer to a number, that number is just going to keep getting bigger and bigger that it spits out, right? Okay, on the flip side, what did you guys get for 0.9? Negative 2997. Oh, sorry, negative 27. And what's this one? Negative 297. Is this negative 2997? Okay, I bet that if we went to 0.9999, a little bit closer, we're just going to get negative 29997. Cool. Now, what we see happening is a really important idea. Until we discussed these rational functions, just really briefly, there's only been one situation where a function can change from being positive to negative. In order to go from positive to negative for a regular polynomial, it must cross over which y value? We're going to rephrase that, and I'm like, you don't have to draw it, but I just want us to think about this because you guys will know this answer. This is the intermediate value theorem, if you don't remember the names of theorems. If I have a function that's negative over here and it's positive over here, guaranteed it must have crossed what? The x-axis. Everybody cool with that idea? Now here's the thing. That only works for polynomials. If you look back at the intermediate value theorem, it said given a polynomial function, this is true. These things, n and d, are polynomials, but because we're dividing by variables at some point when we're looking at these types of functions, the entire function itself is not considered a polynomial. You can't have x in the denominator if it's a true polynomial. This is a new kind of function. Okay, now, with this, we can't divide by 0, right? Like, it just can't work, so x cannot be 1. If we look at this, I go from positive to negative. Is there a root? What do you guys think? If I see my function goes from negative values here, and then all of a sudden it's positive, before we said I had to have an x-intercept, a root, whatever it is, does this one have a root? I see somebody with some intuition. Okay, so check it. Here we are. I have our function graphed, and half these points are missing. I hate that it doesn't let me like size just the little part of it, but we'll try here. All right. Do it there. Quit clicking. Okay. Here it is. It's awesome. All I've done, just so you can see, is I have the original function, and then I started plotting some points. So these are the points that you just gave me. Let's see, and I actually got a little bit closer. So here's 0.5. I didn't go any further, but if I zoom way out, notice what I get. I get another point down here. 0.9 is negative 27. I did not bother doing 0.999. Oh, I did, just kidding. Here's 0.99 at negative 297. and all of a sudden they just kind of look like a straight line. Okay, I am never allowed to divide by 0, which in this case means I'm never allowed to have x equals 1 as a point on my graph. When we do this, and we actually construct our graph, I do indeed see that I go from positive to negative. I wasn't trying to give you a trick question with it, because we were only looking at this section right here. I go from being super negative right here to all of a sudden positive. I had to take a big leap, right? All the way across. There's a secret line hiding in here that we're not allowed to touch. So I'm just going to sketch it real quick. This line seems like the one that we just don't get to touch. Do you remember what we call this? Nice. Asymptote. I think most students kind of like me to some degree. Not everybody, but that's okay. When I was doing my student teaching, people hated me. Like, my kids despised me as a teacher. I was doing 8th and 9th grade, and I don't know, just wasn't, like, I tried to be teacher Holloway rather than just, like, me. Because what you get here is, like, pretty much what I'm like outside of the classroom, except I have a lot more profanity when I'm not in here. Yeah, I don't know, they hated me. My student teacher, the person who helped me, hated me, and I hated her. It was a terrible relationship. Still drives, oh, she was awful. Like, over and over, she's like, you just don't relate with kids. Kids are never going to like you, blah, blah, blah. It's, I despised her. Anyway, I don't remember her name. That's how little I care about her. Like, not even kidding. Not a clue. Can't remember. Okay. However, what I do remember about her is that when we were teaching this, she made fun of me for saying asymptote. Why? Because in her mind, it's asymptote, and it had an extra thing, and it's so stupid, and I'm still mad. Oh my gosh. Okay. All right, it's not asymptote. Okay. As we look at it, though, we are getting to kind of the whole like root of this idea. We have on this function a line or an x value that we get close to that my function blows up, is what I call it. As we approach, and we're going to go back in, and we're continuing the notes from yesterday. So it's weird because there's no main bullet point to start, but that's okay. As we approach for this function, for this f of x, I'm going to say output values, or just outputs, blow up as we get, and then this word we're going to use a lot. I get really close to 1, right? Like on our table, we get within 1/1000th of 1. Could you get closer? Like I can go to 1.000001. Could I get closer than that? Infinitely close. Now, that's a weird idea. You're not wrong, and I like the language. Infinity is big, right? Okay, if you go like really, really close to something, you wouldn't say that you're getting infinitely close because that doesn't make sense. Infinitely, like you're getting large, small, is what you're essentially saying. Like conceptually, you're right though. Infinitesimally small is one word. It's ugly. The alternative, I'm going to say as we get arbitrarily, as close as you possibly want to be, we can still get closer. Arbitrarily close to x equals 1. Now, it doesn't matter on this problem if I come from the left or right, I can get equally close. And this is why this drives me so much like bonkers. This number is really close to 1 from the right or the left, 0.999. From the left. This is really close to 1 from the right. Now, what we see here, and I see different behavior on each side of it. One goes up really fast, one goes down really fast, but they're blowing up in either direction. Okay. Furthermore, this has a name. When this happens, and nice work remembering that, Abigail. As this happens, we get an asymptote. So I'm going to put a little comma here. This is a, and I'm going to be more specific, vertical asymptote. Okay. Last time I'll mention, I promise. Where does the extra syllable come from? Asymptote. I Asymptote.
What'd you say after that?
No. I don't know. It's there's another one that she said that I said wrong, but she was wrong.
Oh.
I don't remember what it is at this point. I'm sure it'll come to me like middle of the night, something.
Where was this?
This was in Gillette, Wyoming. Yep, known for coal and illicit substance abuse. Sorry?
Can you ask for another mentor?
Yeah, but Wyoming's not a very big state, so it was like, I got some good stuff from her. Don't get me wrong; she did teach me a lot of stuff, but she was not a positive influence on my life at that time, not even a little bit. All right, now looking at this, we're gonna define this a little bit more formally. So I'm gonna switch color. Everything yellow that we've written here is with regard to this example that we just worked. If you don't have that possibility, maybe that's a good little thing to add to your notes, just to say, look, now we're just disconnecting. Cool. Let's define this. Now, we are talking about vertical asymptotes currently, but other flavors of these things do exist. So we're going to define asymptotes. Cool. Now, for this, again, there's a few of them. We have vertical asymptotes. They exist. Any other types that you know of? Horizontal? Any other types? Diagonal. We're going to call them slant asymptotes instead. No, now I'm all just flustered.
Wait, so what is it?
Asymptote.
So no 2 Y's?
Did I write it with 2 Y's earlier?
I did.
No, I didn't.
Oh, you did.
No, just that one time I did. Just now I did. I'm not like intentionally gaslighting you. That's not even a word. Nobody's ever said that. Okay. Right? Asymptotes. Now, as we look at these, we have 3 types that we're going to deal with, but we're going to mention 2 of them right now. So, first one, I'm going to use a little asterisk. I'm going to write vertical one time. You will never see me write the words vertical asymptote together again. VA. Short for vertical asymptote. Here we go. Vertical asymptote, the definition of this thing. The line x equals a is a vertical asymptote if, and then we're going to get real mathy. We're going to write it. We're going to talk about it. I'm not going to write all the words down, though. We're going to do symbols. Okay. If f of x, if you hit an asymptote, you're not allowed to cross it, which I'm going to do some sketching over here. Don't draw this, but we can reason this out. Check it out. I want to put an asymptote that I'm never going to cross right here. We'll just put it there for no reason. Now, let's say my function exists on the left and the right side of this, and I'm just making this up as I go. It's possible that I'm increasing as I come here. I only have 2 options as I get closer. My line cannot go through it. Can't happen. Which means this function does one of 2 things. What are the 2 possibilities? It goes up like this, or it could alternatively go downward like this, right? Now, in either situation, there's an easy way to talk about this. If we say it goes up, how far up does it go? Infinitely high. Or without bound is another way you can say that. If it goes downward, how far downward will it go? Infinitely far down, or downward without bound. Do you agree that in this situation, if we have an asymptote, then f of x is going to approach plus or minus infinity? Has to be one of them. Okay. Specifically, as x approaches, and I'll put a letter on here. What do we call this line here? X equals what? A. All right. Now, here's the part that is kind of ugly just to see, and we're going to write both of them, and we're going to talk about it. As x approaches a is the first statement. Now, here's the part. If we look at the graph from before, and I don't need to go to Desmos, but like you'll see it. If I committed to just saying it went up, it's possible that the other one does this. Okay, it can happen. Is it possible that it does this instead? For sure, nothing's broken here. It's still allowed. as we're looking, I can approach A from two different directions. I can approach it from the left or from the right. Do you guys agree with that? Okay. I'm going to add something here. I'm going to say x approaches A plus or x approaches A minus. Any guess on what these are saying? When you think of a positive number, pick a point in your head and pick something more positive than it. What direction on a number line are you? To the right. So when I see A plus, I'm approaching from what side is positive? From the right. As I say x approaches A negative, negative is to the left, I'm approaching my function from the left. So if we look at this graph, and I'm going to put that other yellow line back on it. If we look at this graph right now, and you know what? We're going to define this and then we're going to write a little bit more. Okay, we'll do a single example. Everybody cool with this notation? Positive from the right, negative from the left. Okay, this is calculus notation, just so you guys know. Cool. All right, other part. We never touch vertical asymptotes. Because our function is undefined at this point, you cannot touch it. All right. Nice. The other type that we're going to add in this definition, this will be the only time you see me write this, horizontal asymptotes are the other flavor. Ha is what I use to write those ones down. HA, horizontal asymptote. Horizontal. Yeah, I did. I was already thinking about HA in my head, I think. Although horizontal is a fun way to say it. All right, so we have our horizontal asymptotes. Asymptotes. Oh, cool. Check it out. These ones are a little bit stranger. For this, we're going to say, I'm going to make this really mathy, okay? We're going to claim that the line y equals b, which is a horizontal line, is a horizontal asymptote if, and I want us to think this one out, just like we did before. So I'm going to erase this. And there's a weird little piece. I'm just going to make a graph here, and I want you guys to tell me if you think it has a horizontal asymptote. And it'll have a vertical one too, but let's check it. You know what? Maybe it doesn't have a vertical. Let's say my function does this. Do you think that that graph right there, there's no vertical asymptotes, none. Do you think it has a horizontal asymptote? Riley's gut says yes. Your gut is correct. This thing does have a horizontal asymptote, but there's something fundamentally different about these. When we look at this, if we talk about horizontal asymptotes, we're only concerned with our end behavior, which it's weird to think of, but we only worry about as x gets close to infinity, which could mean a million different things depending on where infinity starts in your mind. While we look at this, all that we're going to say is going to be a similar statement. There's a horizontal asymptote if f of x, my y values, get really close or approach that number b as x gets really close or approaches infinity, either positive or negative. We have the y values getting really close to something as we move further down the x-axis, whether it's in a positive or negative direction. Where this can get weird is if we think of a function, and we're going to do an example, but I want to show you like some of the interesting, what I consider the interesting parts of these. If we look at a function, and there are lots of functions that do this, let's say you think about a spring bouncing. Theoretically, it never stops bouncing. Would you guys agree with that? Like in reality, they do stop, but realistically, it can't ever fully stop. So let's look at a graph like that and say, hypothetically, I want it to follow around this line. Now, we could draw a wave, and we could cover it, and it can go blah. Does this thing have an asymptote? So I hear no. Anybody agree? No. Anybody disagree and think it's yes? I think it does. I think it has a horizontal asymptote. Because even though I'm going back and forth, as I move further down the line here, do I start to mellow out and stop getting closer and closer and closer to that green line? Doesn't matter if I'm bouncing over and below. All that matters is as I get out to infinity, I get closer and closer to this. Doesn't care if it's close above or below, irrelevant. Okay, now looking at these, I don't know that we really need to do an example because we've talked about a few of them and we're going to get other examples. Being able to find these is a huge help in graphing stuff. So we need a way to find them. This is, how do I want to word this? I need your ears and eyes open because there's a lot of stuff here. Okay, so graphing rational functions. That's where we're going. If we think back, we graphed a bit this chapter already. We did some quadratics by completing the square and that stuff. And then we started to factor. Why do we factor? Like, how does factoring help to graph? You find the roots. So if we think about this, if we have the roots of a function, we know the end behavior of this function, and we can find the asymptotes, we would have like everything we need to start graphing super complex looking functions. Okay, we're going to do that, and we're going to do it with these. So I have enough room right here. Do we need to do a little stretch before we jump in? Because I need like 10 straight minutes of discussion. Okay, you're going to think without doing anything calculator. It's a brain break sort of thing. Within the next minute, I want your group to quietly determine the biggest prime number that you can think of. Cool. I'll hook you guys up with stickers for the winning group. 2 minutes. Find me the biggest prime number without Googling it. I'm like just blown away that you guys guessed a big one. Cool. You're only like a billion digits short, or a billion digits short of the biggest one. Sweet. Let's go ahead and talk about finding these. Okay. This is the big idea today. Finding asymptotes. Okay. As we look at finding these guys, only a couple little things that we're going to look at. We need to first let our function f of x be some rational expression. So we're going to say it's n of x over d of x, where, and I'm going to write something before you write it. I want you to tell me that you know what it means. This. That statement, I think you guys can probably tell me what it says, but can you explain the significance of it? First off, GCF meaning, and I'm telling you that the greatest common factor between the numerator and the denominator is 1. What is that, like, why? So what? Now, good that we're having this, because you guys can make sense of that first part, but there's something wonky that happens. We'll dig into it. But if I had a graph, don't write this down, that's just me thinking. If I asked you, and this is factored, to graph this, does anything happen? They divide out, which means their GCF was not 1. Their greatest common factor would have been x plus 1. This expression right here just means simplified, or irreducible if you'd rather, but I'm fine with simplified. Okay, it's simplified so that nothing else can divide out. Okay, if we get that, then we get the following pieces. And I'm going to add a little bit more. Where what is this statement saying? The degree of n of x, good, equals, let's use a lowercase n, and the degree of d of x is equal to, we'll use a lowercase d here. So we have two polynomials written as a fraction or a ratio where there's nothing else that's going to divide out and simplify, and we can identify the degrees of them. We need a lot of information, and there's a lot of pieces to put together just to start. Okay, first one. This one's easy. Part one of this whole rule, and they're not in sequence. This is just, I have 1 and 2. You don't have to use these letters if you don't want to. First one, the graph of f, and we'll even say the graph of f of x, has vertical asymptotes. And let's think back to that example that we looked at initially. We saw in that table that our function blew up to positive and negative infinity, and it happened when we tried to divide by what? As we got closer and closer, and I can go back up, as we got closer and closer to dividing by what number would be in the denominator? 0. We're getting really close to dividing by 0, which makes our number big. Because dividing by something really small makes it blow up. Okay, the vertical asymptote happens when we try to divide by 0. What part of our function, as defined above, do we have to worry about being 0? N of x or d of x? So 0 in the numerator is okay. 0 in the denominator is not. So turns out super easy. The graph of f of x has vertical asymptotes at the zeros of d of x. Now, just to show you that we've already covered 90% of this, is it possible that d of x is a big ugly polynomial that we can't group and we can't shortcut and stuff? You might have to PQ list it to factor it to find those zeros. That's okay. They will show up. Okay, so automatically the stuff that we've been talking about for last week is applicable. Vertical asymptotes are easy. Okay, that's it. That's all I have to say about those. The second one, and I guess I lied. I'm going to make a little statement here. Could have one, could have none, could have many. Second part. The graph of f of x has horizontal asymptotes which are found the graph of f of x has horizontal asymptotes which are found by comparing degrees. Now, we've already hit this above. We said degree of the numerator is n and the degree of the denominator is d, just to work this out. Okay. Is it possible that the numerator has a larger degree than the denominator? I think so, right? Just to show you guys, and I'm going to generalize this, and the homework's going to be super chill. If I want to think about that, check it out. X to the 5th over x to the 4th plus 1. Degree of the numerator is 5, degree of the denominator is, and nothing simplifies out because you can't just deal with part of it. It has to be everything. This is one of those situations. Maybe in option 1, we're just going to say that, and I'm going to put a star. Do you want me to write degree n greater than degree d, or can I just say, because we've written it above, that the degree of the numerator n is greater than the degree of the denominator d? Are you cool with the shortened version here, since we already said what n and d are? Okay. If this happens, let's just think about it. I know that this is going to simplify eventually, but we're going to use an easier one just to think about it. And let's have x squared over x. In reality, that would simplify, right? But if I put a plus 1 or plus 2 at the end, then it won't simplify because it's just sum of squares and it's ugly. Let's pick a big number. We're just going to start getting closer to infinity. Pick a number. 10. What's 10 squared divided by 10? 10. Okay, pick something bigger than 10. Okay, 100. Cool. 100 hundredths is 10,000 divided by 100 is 1,000. We just went from a value of 10 up to 1,000 just now. The numerator gets bigger way faster than the denominator. Do you guys agree with that? A whole power of 1 faster, in fact. That means that, is this thing ever going to keep getting bigger and bigger and bigger? No matter what, the numerator gets bigger faster because of that power. The denominator never catches up, which means that number is just going to keep growing. If this happens, this is what we want. If the numerator has a larger degree than the denominator, then, did it ever stop getting bigger? I don't think so. No horizontal asymptote. If your numerator is bigger, no horizontal asymptote. Okay. What's another possibility? They could be, numerator could be bigger. Something else? I couldn't read your lips, but I saw your lips move. Could be less than. I'm going to save that one for down here, but we'll do that one right now. Certainly possible that n is less than d. Now, keep in mind, if you'd rather, you could say the denominator is a larger degree. We could switch that inequality around. Okay, if this happens, also super easy. In this situation, and we're just going to, would you rather look at a graph or an equation? Equation. Okay, not what I was expecting, but I'm cool with it. Okay, let's think about what happens if the denominator is bigger. Let's do 2x over 5x squared. And I lied, we're just going to do it over x squared because that's easier. And we're going to assume that there's other stuff that just doesn't factor, but the powers grow fastest. Let's pick 1. 2 over 1 is 2, right? Okay, sure, it didn't get bigger. Let's pick something bigger, 5. 10 over 25 is our new number. Are you guys cool with that? Is that less than 1? That's 2/5. So we're at 0.4. Let's pick 10. 20 over 100 is what it would spit out at me. That's 0.2. Okay, let's pick 50. 100 over 2500 is now all the way down to 0.04. My numbers keep getting smaller. They're going to get smaller and smaller and smaller. So small, in fact, that arbitrarily close to what? 0. If you have this situation, then horizontal asymptote, super easy to identify. No thinking needed. The horizontal asymptote, HA, is at the line y equals 0. It's just the x-axis. Or a push up or down, but we'll see that. Okay, there's one weirder spot though. Why did I leave a gap? They could be equal to each other. Okay, this one, I have to use a graph. But we're going to see if we can reason it out. So I don't care what the degree is, and I'm just going to clear all of this stuff. And let's take a look. If they're equal, this is a third possibility. Now I'm going to have to do it so they don't simplify. I'm just going to say y equals x to the n plus 1 and y, over, x to the n plus 1. And then underneath, or over, and we'll just do this nicely, over x to the n, and then we'll do the plus 1 here so that I know they won't simplify. Okay, if we look at this, what value am I getting really close to as I move really far to the right or really far to the left? So here we go, really far to the left. Are you sure it's 0? What y value am I getting close to? Seemingly getting close to 1. If I come over this way, what do you think I'm getting close to? Okay, so notice though, and I'm going to steal this back down here. Okay, I'm going to only make one little change. It gets close to 1 there, right? And it doesn't matter what n is as long as it's fairly large. Okay, so all that's going to change is that shape. Okay, stop it. There we go. All right, let's get a little wild here. I am going to make that back to 1 because it's going to drive me crazy. What if I make this a 4? As I move really far to the left, what y value do I get close to? How about really far to the right? Is it going to 4 again still? Okay. I'm going to put a 3 down here. This one's a little bit harder. What does it look like I'm getting close to? 1 point. What do you guys think? Do you agree it's 1.3? How about to the right? 1.3. When I change the coefficients, it changes where my asymptote lives. When it was 1x to the n over 1x to the n, the coefficient, or the horizontal asymptote was at line y equals 1. If I make it 4 over 2, any gut feeling of where it's going to be? 2. Hey, it is at 2. How'd you do that? You divided, and specifically you just took the ratio, right? Now, If you don't see it, you can verify. If this happens though, the horizontal asymptote is at the line y equals, and this is going to be the ugliest fraction we ever write, the leading coefficient of n over the leading coefficient of the denominator every single time. It could be ugly, but it might not be. This is our horizontal asymptote. Now, your job, and I'm trying to decide where I want to go with it. Cool. We have 10 minutes. Oh man, this stuff is so fun. Sweet. All right, here's what I want us to do. We are going to jump in the deep end together. Cool. This, I'll tell you, is from this section. I'm going to argue that this is like the most important part. Like, this is everything that we need. We're going to do some more stuff on Monday as well. This is like the real part of the lesson, though. The rest is just practice with this idea. Okay, so let's do a few problems together real quick. We're going to sketch a function. And we're going to start graphing these ugly things, but we're going to take it step by step. So here we go. Example. And we're going to graph one together. Graph. And then I might not give you homework over the weekend. We'll see. Cool. We gonna do some graphing. Specifically, I want us to graph the following. Let's graph f of x equals, let's get real crazy, 3x squared plus 7x minus 6 over x squared plus 4x plus 3. All right. We're going to break this down into parts, and realistically, some of this might be your homework, which I always say, like, hey, I'm going to check your notes tomorrow. I really will on Monday if this is what winds up being the homework, okay? Like, we need practice with it. You have a long weekend. I don't want you to try to forget everything right over the weekend. So part A, I want you to factor and simplify. Cool. So, let's divvy up the labor. Who's the coolest person in this room? Okay, Abigail had the right answer. That side of the room, you get to factor the denominator.
Wait, what?
Nobody's in trouble for anything, but you guys are factoring the numerator. Cool. Your numerator. Denominator group, if you finish early, help with the numerator would be cool.
For what? Okay.
Love what you did. Write your number. We'll get there.
Okay.
But I want to catch up with you.
Okay.
You guys should know. Or the numerator. Alright,
Seven
skip practice. If you're like stellar at factoring.
or 6 and 1. 7.
Well, careful. What? 3 times 6?
Oh, 18.
18? Negative or positive? Negative. So we need factors of 18 that add up to what?
7.
To positive 7, right? And negative 18. I bet it's negative 2 and 9.
Oh, he's not.
I thought you usually made the big number negative.
Only if they have to add up to a negative. Because these ones have to add up to a positive. Yep, and I just switch them. Okay, so a little bit of grouping going to happen. I'm just going to do it right here. 3x squared minus 2x plus 9x minus 6. And then probably without finishing the problem, we can see the factorization. What comes out of this one? An x, what's it leave behind?
X and 2.
A 3x minus 2. And this one? 3, and leaves behind a 3x minus 2. Okay, so check it out. We have two factors. X plus 3. And what was the other one? Now, write it all. Even if you're going to simplify it, because I do think something is going to simplify out, because when we're doing this, we're getting our domain right now. What numbers am I not allowed to divide by? 0. That's the only number. Are there values of x that even after simplifying, are there values of x that would make me divide by 0 right now? So the look on your face specifically, and maybe I'm just not reading, looks like maybe you're not confident in this. I can't tell. This question is so much easier than you might think, and if I framed it in a way that made it hard, that's my bad. What values of x make the bottom 0? -3 does this one, and this one? -1. So check it out. We just answered the domain. Every x value except those two work. Like, we have our domain. Now, there's going to be more parts of it, but let's keep simplifying. What falls out? Or divides out? Okay, which means our end expression is just this guy. 3x minus 2 over x plus 1. Now, we're going to address this on Monday as well. I'm going to make a note right inside this example. There is a hole in or on, probably on the graph at what value just divided out? So that's the factor that divided out. What x weren't we allowed to use that just fell out? There's a hole in our graph at x equals -3 and whatever f of -3 is. You can't actually plot the point because it's undefined. There's just going to be a hole, and we'll see this when we graph this to finish up. Okay, so this is our factored form. Easy. All right, can you tell me, just with words, can you tell me the degree of the numerator and denominator? Degree of the numerator is 1, degree of denominator is 1, piece of cake. So, part B then is I just want to know, are there asymptotes? I think there's a couple, at least one. How do you determine if there's a horizontal? Or sorry, a vertical? Louder? So careful, vertical. It only is going to happen when we have our simplified poly, when we do what? Thought you were already talking, sorry. So let's see. So vertical asymptote, if, I bet we have it right here as well. So read this one. The zeros of my denominator. What value of x makes my now simplified denominator 0? -1, right? Because it's simplified. Check it out. That's it. Vertical asymptote. X equals -1. Easy. The zeros of the denominator. That's it. The horizontal asymptote can be a little bit harder. But if we have that list and you're able to reference it, it won't be. They're both degree 1, right? What's the leading coefficient of the numerator? 3. What's the leading coefficient of the denominator? What is 3 over 1? Okay, check it out. There it is. We now have our asymptotes with these guys. Okay, we have vertical asymptote. We have a horizontal asymptote. Cool. Last little part of this. This is your one little part of the homework. On C, I want you to relax this week, and we'll continue this problem on Monday.